Hey, welcome back to Dr. Pat TV, looking at limits. So this is part two of our limit idea. Okay, so now in the previous video, we were looking at a couple of functions. The functions that we were looking at before had holes. So this is a second example, the second type of thing that can happen when we're dividing by zeros. We can create something we call vertical asymptotes. All right, so now with this particular function, when we plug in -3, we plug -3 in there. Of course, what's going to happen to us is we're going to have 0 in the denominator. Of course, that's a bad thing to happen. Things get kind of weird, get a little funky going on there. So let's kind of explore this one for us. Now, when we're doing limits, okay, again, recall that limits for us math people, they're really great. They're like our duct tape. They really help us work through some problems to see if the function's going okay. Is there what the y value is? What's the function doing? What's the y value? So that's what this is all about because we know the x value. In this case, our x is going to -3, so we know where we're looking. We want to know what this function's doing. If we look at it graphically, and here's our x equals -3, when we look at this graphically, we do not get a y value. It's undefined because of the 0 in the denominator. But in this case, the graph does something kind of, funky here because it's not going smoothly along and it's just got a little hole in it that we can patch up. This one's got some problems here is because on one side of -3, this thing's zooming off to infinity, and then on the other side, as we get close to -3, this thing's going down to -infinity. So this is an example where this one's just kind of not working right for us. It's not very good for us. Okay, so that's what we're creating here is a vertical asymptote, that vertical line at -3 in this case. And we're undefined there, and the graph is zooming off to infinities. Okay, so now what's happening here, or how can we see this numerically? What I'm doing here is I plugged the function into the calculator. I'm using my table feature. And then I just started plugging in x values. As you can see, these are x values that are getting closer and closer to -3. At -3, the calculator gives me the error message, which is good because it's supposed to be an error there because of the 0 in the denominator. The catch thing is that as we get closer to 3, what is happening to our y values? In this case, hopefully you can kind of recognize the pattern. Our y values are just getting larger and larger and larger. And that's that zooming off to infinity, positive infinity. This graph is going larger and larger, going up and up and up, getting larger y values. And if I didn't have the graph and I just did the table of data, that's telling me also. So I can look at this graphically, I can look at it numerically with the table of data, and I can see things are not working for us. The values are just getting larger and larger and larger. Then basically what we describe this as, the limit does not exist. So DNE, this little DNE kind of thing going on here, just means does not exist. So that means what we're saying is that the limit, there's no nice number that I can fill in, I can patch in for the hole there. And so what's happened algebraically? We're going to use the same idea, two steps if we can, simplify the expression and then evaluate. In this particular example, when I'm working it algebraically, I'm going to simplify it, so I'm going to factor the top. But when we factor the top, unlike the previous examples, there's nothing that reduces out. This is an x plus 2 on, and this is an x minus 3, and x plus 3. There's nothing that's similar that I could reduce out. So I'm stuck with that 0 in the denominator. So when we have -3, I am stuck with it because I can't reduce this out. And when we can't reduce out, that's a problem for us. And that's when we have limits that don't exist. It's all because our algebra, we're not able to simplify this, reduce this, and to kind of eliminate the problem that we have. And so in this case, that's how our vertical asymptotes happen, is when the things don't factor out for us. Okay, so let's do a quick recap. In the first video, part 1, I did these two examples right here. They created holes. Which basically means if we picked the right point, we can patch it. We can find out what the y value was. We had distinct numbers that we could have. And why was that? Was because we could simplify these. We could factor these expressions, and then we can reduce out the denominator. where the problem was. In this second case where we got a vertical asymptote, I'm calling that VA, how did we get a vertical asymptote? It was because algebraically we could not factor and reduce things out. So when we can reduce things out, that's great, that's good. We get a whole, we get a limit, we actually get a number. When we cannot reduce it out algebraically, our limit does not exist. We don't get a number. So that's the kind of a quick little recap there. I do have another idea that we have to cover, left and right limits, and that will be in the next video. Thanks, and have a good